now the now we are applying some boundary condition at time t equals to 0. The system is in state 0. Then pk 0 equals to 1 for k equals to 0 and 0 for k not equals to 0. So this particular boundary condition we will represent like this. With this condition, we now applying these particular boundary condition on these equations, we solve the particular differential equation. So now applying the boundary condition in both these equations, we get dp naught t upon dt equals to minus lambda p naught t. Now we will get dp naught t upon dt equals to minus lambda p naught t. From this expression we get, after integration, p naught t equals to e minus lambda t. So this value we will get p naught t equals to e minus lambda t after applying the boundary condition. Now this value of p naught t applying in these equations, this value of p naught t applying here. So now we will get the expressions for Poisson process. The first one is, we have the equations dpkt upon dt equals to lambda pk minus 1 t minus lambda pkt for k greater than equal to 1. If k equals to 1, then dp1t upon dt equals to lambda p naught t minus lambda p1 t. This p naught t value we will put, then dp1 t upon dt equals to lambda p naught t. We have already the value of p naught t, which is e to the power minus lambda t minus lambda p1 t. After solving this equation, we will get, solving this equation, again differential equation. After solving this equation, we will have p1 t equals to lambda t e to the power minus lambda t. p1 t, we have the value of p1 t. Solve for k equals to 2. Now we will put k equals to 2. For k equals to 2, similarly the value of p2t equals to lambda t the power e to the power minus lambda t upon factorial 2. Similarly we will put k equals to 3, k equals to 4, k equals to 5. Finally we will get the general solution for this equation, which is pkt equals to lambda t to the power k e to the power multiply by e to the power minus lambda t upon factorial k. After solving all the equation, we will get pkt equals to lambda t to the power k multiply by e to the power minus lambda t upon factorial k. This equation is the most calibrated Poisson arrival process equation. So this is most important expression, pkt equals to lambda t to the power k multiply by e to the power minus lambda t upon k factorial, which is the Poisson arrival process equation, which we will get after, first of all we have a pure birth process. Then in pure birth process we will put termination rate equals to 0. After we will assume a constant arrival rate or birth rate, which is lambda, and after that whatever the expression we will get, we solved by boundary condition, and finally we will get pkt equals to this one. This is the our final Poisson arrival process, which is the most calibrated Poisson arrival process equation. Now we will discuss about case 2, which is now we will discuss about our case 2, which is pure death process. As the name says, pure death process, it means in this particular PD process, or we can say that it is a special case of birth death process in which the birth rate equals to 0. Birth rate equals to 0. So there is no birth occurs. It's only about the termination. So this particular process is known as pure death process. For pure but death process, now we have to obtain the equation governing the dynamics of a pure death process. To to obtaining the equations for governing the dynamics of pure death process, we will put lambda equals to 0. After putting put lambda equals to 0 in equation 1 and 2, so after this we will get dpkt upon dt equals to mu k plus 1 pk plus 1 t minus mu k pk t for k is greater than equal to 1. And the second expression we will get p naught t upon dt equals to mu 1 p1 t. So these both are the expression for pure death process. For first one is for k is greater than equal to 1, and second one is for k equals to 0. Both the expression we don't have the lambda term, because lambda already equals to 0 because it is a pure death process. So now let now we assume that the death rate is constant. So it's all about mu. It is independent of state. So now the expressions are dpkt upon dt equals to mu pk plus 1 t minus mu pk t for k greater than equal to 1, and the second one is d p naught t upon dt equals to mu p1 t, which is for k equals to 0. We have both the expression whenever death rate is constant. Now we will solve the particular expression after applying the boundary condition. So to solve the applying boundary conditions, so let our boundary condition is let at times t equals to 0 there are n numbers in population, or numbers in population, or we can say that n members in population, we then obtain the equation dpkt. First of all, we will assume this boundary condition. Now applying the particular boundary, dpkt upon dt equals to mu p k plus 1 t minus mu pkt for k lie between 0 to n. Now if if k equals to n, the expression is dpnt upon dt equals to minus mu pnt. The all are the particular boundary condition as per the boundary condition. Third one is dp naught t upon dt equals to mu 1 p1t, sorry, mu p1t for k equals to 0. This expression already we have. First one, both the cases we will coming from this expression by applying the particular this boundary condition. Now we have three equations. After applying the boundary conditions and solve these equations, finally we will get p and t equals to e to the power minus mu t for k equals to n. Second one is pkt equals to mu t to the power n minus k upon n minus k factorial e to the power minus mu t for k lie between 0 to n. And last one is p naught t equals to mu t to power n minus 1 upon n minus 1 factorial e to the power mu t for k equals to 0. All these equations for pure death process. So finally we will discuss our all topics: birth death process, both the cases of birth death process, pure birth process and birth death process. Under birth death process we have two cases. First one is pure birth process and second one is pure death process. Thank you very much.